Alright, so this is the first lecture video of the semester, which we do start in Chapter 6. We start the first 8 weeks of the semester doing counting, probability, and statistics, and then the second 8 weeks we do other stuff. Alright, so 6.1, so hopefully you went on ReggieNet and got a copy of either a hard copy or a tablet or something. You should, makes it much easier if you have a copy of these notes right in front of you. Alright, again, it just makes life easier if you do that. Alright, keep in mind these videos are new. Alright, this is the first semester that I've gone completely online for this particular class, and so I'm only human. More than likely I will make errors. Alright, again, just let me know and I'll try to fix them. It's a work in progress. Alright, Chapter 6. Chapter 6 is a very important chapter. It's on counting sex, counting things that happen in an experiment. Right, and again, we're just basically going to be counting stuff. Counting is very, very important. Alright, this chapter 6 is vital because it lays the foundation for the things we're going to do over the first 3 chapters. Alright, chapter 6, 7, and 8, which will take us through the first half of the semester, the first 8 weeks of the semester. Alright, so again, this is a very important chapter. Make sure that you understand chapter 6 because it'll make chapter 7 go a little smoother and chapter 8 go a little smoother. Alright, math tends to build on itself, and this is one of those sections where it really does. 6 is, like I said, the foundation. Alright, let's get started. Alright, 6.1 video 1. Alright, so this is the first video. Again, you have all of the notes there. We'll break it down into smaller segments. For you to, watch little clips instead of a big long lecture all at once. Alright, so 6.1 is sort of the basics. Alright, we're going to get started in a lot of notation. Math is a language. Alright, we use our own notation, our own terminology. It's what it is, right? Derivatives, operators, sets, all of those things, unions, all have rules. And in mathematicians, we like to shorten a lot of stuff. So there's a lot of notation that's built into mathematics that you have to be able to read and interpret. Alright, so that's sort of the first set. The first thing we're going to do here is a lot of reading and interpreting some math notation that has to do with sets and operations that are done to sets in order to get to count them. Alright, first, I've been using this term set. Well, what is a set? Basically, the simplest definition is it's just a well-defined, now there's that term well-defined, collection of objects. And we usually use capital letters in this class to distinguish what a set is. Alright, so an example, we'll say set A is even numbers, or even integers, between 0 and 10. Alright, and so there's my definition, there's my define, and the objects are, well, we say set A then, and set notation is grouping symbols, and that's a horrible grade. You have to bear with my tablet writing isn't the best. Alright, grouping symbols, and then we list them. Alright, so what are the even integers between 0 and 10? Alright, and I'm going to include 10. It's between 0 and 10. I assume we're including 10. Alright, so 0 is neither even nor odd, so the first one is 2, then 4, then 6, then 8, then 10. There's my, again, end of set notation. Another example would be, we're going to do experiments, alright? So an experiment would be set B, so I'm going to write up here, give me a second. Set B would be all of the outcomes when I flip a coin, alright? So B is the set of all outcomes when a fair coin is tossed. Alright, so B, well, the outcomes when a fair coin, meaning it's a heads and tails, it's fair. And so when you flip a coin, you can get heads or tails, and so those are the two possible outcomes. So heads, tails. And usually we'll simplify that further, and we'll just do H and T. H stands for head, T stands for tails. So right now I'm going to leave it heads and tails. You can get even more descriptive. You can do a collection of people. We could say set C is all freshmen at ISU. All right, now I can't list those because I don't know them all, though there's probably a list of it somewhere, and that would be the name of every freshman at Illinois State University. All right, you could even make it smaller, a name of all female freshmen. All right, so again, it's just a collection of objects, and it could be people, things, or events. All right, or numbers. We can do a lot with numbers in mathematics. All right, so a set, just a well-defined collection of objects. We usually use capital letters to define what they are. All right, to write what they are. All right, elements. An element is an object in a set. So it's one of the, or a multiple of the, objects that are in the set. So the notation of this is what sometimes is weird. So I'm going to write down my set A. So remember, set A was the numbers 2, 4, 6, 8, and 10, right? It was the even numbers, even integers between 0 and 10. All right, so there's my set A. All right, 4 is an element of set A. All right, 4 is an object that's in set A. It's an element of set A. Heads would have been an element in set B. All right, now mathematicians like to shorten things. All right, and so what we do is, well, we have notation for that phrase, since it's a phrase we use a lot in mathematics. All right, and a lot of times we'll use Greek or Latin stuff, and so this is actually a Greek letter that we use. We use 4. It's a sigma, not sigma, epsilon. But that notation, it's a Greek letter, and basically that Greek letter means 4 is an element of set A. All right, so we shorten, instead of having to write out the sentence, this is an element of this set, we use that Greek letter in order to do it. All right, so 4 is an element of set A. Heads was an element of set B. All right, so this would mean math is its own language, right? Instead of writing, and we like to shorten everything. Mathematicians like things that are short. Scientists like things that are short. Notation, that we kind of compact it in short things. All right, so that symbol is element of. Heads is an element of set B. 4 was an element of set A. 10 is an element of set A. All right, and so element of, and notation you have to recognize. All right. Set B is equal to set A, denoted with an equal sign, if set A and set B contain the same element. So an example would be, so I'm going to use my same set A I had before, but a different set B. So set A was 2, 4, 6, 8, and 10. All right, in order to be equal, it just has to have the same element. So as long as it's got the exact same elements as set A, it's equal to it. And I wrote them in a different order. I wrote 8, 6, 2, 4, 10. But they are equal. A is equal to B. Right? Because they contain the same elements, even though they're in different orders, they're still the same set. All right? They're equivalent sets. Alright, subsets. There's 2 types of subsets we're going to look at. So we're going to do this as the general subset. B is a subset of A, of set A, if every element of B is also an element of A. So it means every element that's in B has to also be in A. Now A could be the same as B, or A can have more elements than B. Alright, and so the notation that we use for this, we say B. It's sort of a sideways U, and then there's this little line underneath it. All right, and what that means is it's giving me equal. It's kind of like the less than or equal to notation, right? 2 is less than or equal to X or something along those lines. It allows equality, meaning B could be a set smaller than A, or B could be the same as A. All right, so an example again, my set A, well, I'm going to do the same set A I had before, 2, 4, 6, 8, 10. That same set B I had before. I've done it in a slightly different order, but this is true. B is a subset of A because equality, that's the equal sign. That little line underneath means every element of B, right? 8, 6, 4, 2, and 10 is also an element of A. All right, I'm going to put another set in here. I'm going to say set C. Again, my notation for my set notation is getting a little wonky. Alright, so set C is the set of just the numbers 6 and 8. So C would be a subset of A, well, C would also be a subset of B. Alright, because every element in C shows up in A, and every element, and so this is the case where they don't have to be the same. They could be the same, but they don't have to be the same, as long as every element in my subset is also in my bigger set. Alright, again, like I said, you could also have equality. You don't have to, right, but you can. Alright, so that would be the general subset, which allows equal to. Alright, the next subset is what we call a proper subset. So a proper subset, alright, so B is a proper subset of A if every element in set B is also an element of set A, so it's the same line as the subset we had above, but then there's this additional piece. Set B cannot be equal to set A. Alright, so set A must have more elements than B. Everything that's in B has to be in A, but then A has more. Alright, so the notation is, well, we just drop the equal to sign. Alright, we just draw that sort of sideways U. So B is like the strict equality. It's 2 is less than X. We drop the equal to. There's no equal to here. B cannot be equal to set A. Alright, so I'm going to do my same set A I had before, but a different set B. So 2, 4, 6, 8, 10, because I can't use the same B I had before. Alright, so I've got set A, which is 2, 4, 6, 8, 10. And then I've got a new set B, which is just 4 and 10. And it is a proper subset then. B is a subset of A, and they aren't equal to each other. Every element of B is in A, and A has more elements than it. Alright, if I do that same C I had before, I can't remember what it was, I'm going to do a new C. Alright, that would also be, C would also be a subset of A. It's not a subset of B, because they're not the same elements, but C is a subset. It's a strict, proper. Proper subset means they can't be equal to, and every element in the subgroup has to be in the big group, and there has to be a bigger group, meaning the A has to have more elements in it. Empty sets. Empty set, you should have heard of empty set before. Basically, it's a set containing no elements. Empty set is always a subset of any other set. Right? Empty means nothing. There's nothing in my group. So the empty set is either grouping symbols with nothing in between, or more common, we write the no solution symbol. No solution means the solution set is empty. That's what it means. It means when there's no solution, the solution set is empty. And so the notation for that is a 0 with like a cross through it. That's the empty set is the no solution set. Alright? There's nothing inside the solution, right? There is no solution involved, which is a perfectly fine answer in mathematics, all right? It's one we don't like to get, but it is a perfectly fine answer. And nothing, they say this empty set is nothing, is always a subset of something. And it can also be, again, a general or a proper subset. So nothing is a subset of a group with something in it, right? It's kind of one of those weird things, but it's true. Alright, in this class we're going to be finding universal sets and subsets. Alright, so the universal set, we either denote it with a capital S or a capital U, typically. We don't have to. We just typically do it that way. And the reason why, well, U should be obvious. U would be universal set. The reason why S is used is because when we do experiments, we call it a sample space. And the sample space represents all possible solutions, all possible outcomes. And so that's why capital S is used. And basically, it's just the set of all elements into consideration. If I said the real numbers, all right, we're interested in all the real numbers, that would be the set in consideration. Or all even integers, that would be the set into consideration. All math majors that live in the dorms, all right, that would be a set under consideration. All right, so now we're going to do an example just kind of practicing true and false statements. A lot of times these will be done as true and false types. Alright, so this is an example of just getting you used to reading and understanding the subset notation. Alright, so S is my universal set. So this is all my numbers in consideration. This is the universal. So it's just the numbers, the whole numbers, 1, 2, 3, 4, 5, 6, 7. We don't want any other numbers but those. All right, those 9 digits are it. All right, then I've got subsets. All right, E is a subset. All right, this is the notation mean my number n, so n represents a number, where n is a positive even integer less than 10. All right, positive even integer less than 10, right, which that means it does fall in my group. A, B, C, and D are all subsets. Those are all whole number values that are between 1 and 9. All right, so we want to answer the following if these, so we want to know, are these subset statements true or false? All right, and then while I'm doing this, like usually in a classroom, I would kind of open it up and let the class answer. So try to answer it before I do. All right, as working through these guided notes, or guided, and you should be sort of answering some of the stuff before I get to it. All right, and so we'll see if you can't answer it before I do. Okay, so the first one is D a subset of A, and they could have equality? And so remember, to be a subset, all the elements in D have to show up in A. Well, D are the numbers 4 and 7. A is the numbers 2, 4, 6, and 8. And so that's false, right? Because 7 is not in set A, and so that one's a false statement. B. Is B a subset of S? Well, I should check it. I said that it was, but you should make sure if I said what it was, it really is. All right, so B is the numbers 3, 4, 7, and 8. S is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, and so all of those land between 1 and 9, and so that checks. That's true. All right, I kind of said this a minute ago. All right, the empty set, right, that's the empty set notation, is a subset of C. Well, empty set is always nothing, is always a subset of something. All right, the next one we're looking at is set A and E. All right, there's going to be the next 3. We're going to deal with set A and E. So A is the numbers 2, 4, 6, and 8. E is a set, instead of writing out what it is, it was a descriptive set. But let's see if they're the same or not. All right, so I'm going to list what E represents. So E are the numbers that are positive, even, and less than 10. All right, so positive means bigger than 0. Even, 2, 4, 6, 8. Smaller than 10, 2, 4, 6, 8. Right, and the E is the same, right? Those are all of the numbers that are positive and less than 10. Positive, even, and less than 10. And so it's a description of the same group that set A was. And so set A is exactly the same as set E. Just one was where we listed it, and one was more of a verbal or written description, not a verbal description. And so it's true. A and E are the same, right? A and E have the same elements. So that's true. All right, is A general subset of E? The general subset means I have this little bar underneath it, which means they can be equal to, right? Everything in A is also in E, and it can be the same. That's true. All right, because the previous statement is true. All right, but the next one, set F, or question F, is A proper subset of E? Well, remember, to be a proper subset, every element in A has to be in E, and that's true, except A cannot be equal to E, right? E has to be bigger. And so it fails because they're equal to, all right? So that's false. All right, G, is B a subset of D? Well, that one's easy to answer false because subsets should be a fewer, right? D is 4 and 7, B has 3, 4, 7, and 8, and so that's false. All right, every element in B is not an element in D. All right, flip it around though, write it the other way. Is D a subset of B? Well, D, every element in D has to be in B, and they can't be the same. Well, the D is 4 and 7. B is 3, 4, 7, and 8, and so that checks. Every element in D shows up in B, and B is bigger. There are more elements in B than set D, and so that's true. All right, the next one, is it a general sub? Well, if it's a proper subset, it's a general subset, so that's also true. It just allows you to have equality, it allows you to have more options. Are B and D equal? Nope, they are not equal because B has more elements than D, and so the last one is false. All right, so hopefully, all right, you practice recognizing and understanding the notation. Really, it's a lot what this one is notation. Most of you have talked about somewhere about sets and groups and subsets, but maybe not worked with the notation as much. So maybe practice reading and writing and understanding the set notation. In the next video, alright, so we're still in 6.1, as we kind of break it down into smaller sentence instead of all at once at you. I think I do this in like 3 videos. The next video will be over Venn diagrams and set operations, and that's a big one. Alright, that's going to be a big one to make sure that you watch and maybe rewatch. Alright, and that'll be the next video. Alright, we're going to stop it there.